Greetings. This is a quick overview of the design of a test bench system for the validation and the visual inspection and the weld strength detection of a sample bridging unit. This is a design which includes a singular test bench with a rack for the different parts, of course a compressor, a fan to keep the subsystems cool, a toolbox, of course a local SCADA system, controller units of course here. These are the robotic control units. Of course, there will be two of these, FRL units, direction control valves, power supply units, the overall frame structure. When we come to this side, we can see variable frequency drives, servo controllers, and of course stepper motor controllers as well. As part of this design, you will see that there is a singular workpiece carrier that can be accommodated, of course each station. We will see infrared proximity sensors. We will see a plunger, that is a stopper with a corresponding cylinder. We see a SCADA robot, selective compliance robotic element. We will see a synchronous motor assembly for the driving of your conveyor belts, which is connected of course to the variable frequency drive. That is station 1. The purpose of which is to use this weld test probe, as we can see, to go terminal wise and to check for weld strength via ultrasonic imaging. Of course, here at this station we have nozzles that blow out air onto the parts and the workpiece carriers themselves. This is the stopper, fully retracted. As you can see, this stops the workpiece carrier as a whole. Once the part reaches here, the parts are lifted and they, as you can see, they are placed right here into the circular hub by this gripper, which is mounted onto a gantry system, which is mounted onto the desk. Once this is completed, of course, the parts move to the next station where once again, of course, we will have the plunger retracting out and we have a camera, a Keyence camera to scale that is mounted onto a corresponding customized bracket, which will see at every terminal what is the problem and inspect the part as a whole for short modes. This is of course a flash unit, which will ensure that the corresponding luminous intensity is available. So this is the screw compressor to provide the requisite air supply via the FRLs to the direction control valves. These are the valve manifolds. The wiring and the pneumatical piping is not included in the CAD and it is a question of real-time implementation. Of course, in parallel, the same design can be scaled to a shop floor layout as well. A simpler shop floor layout will of course be seen right now on the screen. It's loading. Okay, so here we have with us the shop floor layout in front of us. 4 cells which are laid onto the shop floor. This is the gangway, operators. Of course, we have another local SCADA system. And of course, here in this model, we can also see a master server element with appropriate cooling systems with the master computational elements inside, which has the sufficient hardware power in order to run, let's say, artificial intelligence detection codes and also be powerful enough to facilitate real-time OTA data transfer. In parallel, I can close this and see how this could look like in a shop floor layout with, let's say, a covering as well. This is one thing I will open now, shop floor layout with covering. In this layout, we can see the same with an enclosure with walls. And of course, I've also included as a nifty touch, an automated guided vehicle AGV inside. We just wait as it loads. And it's done, downloading. In parallel, of course, we can check the shop floor layout test bin station. This is, of course, the shop floor, how it looks like with an enclosure. This is an automated guided vehicle. The theme of the company is preserved, the green color, light green color on gray and chrome. Of course, to show an IoT-based framework has also been seen here. Of course, going back to the actual CAD model, for the singular station, we also have a quick overview of the functionalities, which can also be seen. So let us run through the process. So we can see a workpiece carrier come into place. The plunger has extended out. The ultrasonic weld probe moves from one terminal to another terminal. The locations are, of course, encoded as per the corresponding coordinate system made with the SCADA controller. As this process happens, in parallel, we have the camera station that keeps inspecting at first stage or first pass each terminal for the quality of the silphos. This is in correlation with the silpho detection model that we had seen earlier. Once this process completes, the alignment, everything is controlled by the motor and the corresponding power units with the SCADA robot. The process keeps continuing, and now the process is completed. Now, once this is done, we move on to the next process, which is the next stage of camera inspection, which we can clearly visualize at this point. So we will now start running the same, and here we go. So the workpiece carrier stops at a certain location, the part is lifted up, and as we can see, the camera starts inspecting at the appropriate locations. So once again, maybe a very quick update on this topic. Moment. So we will reset position. So everything is okay. Recalculate, stop, go back to position 1. Save the controller configuration. We go back to make controller 2, edit the feature, and now we check what happens when I, let's say, go to an individual position. So let's say I go to position number 8. So we can now see it's okay. Go to position 17, 13, position, all is good. So let's go back to position 1 and let's start simulation. So quickly we can see part is lifted up. So the part configuration is now proper. The camera is properly configured. The camera will check each location for any problems. Of course, it will check underneath the part for any kinds of short moles. Zoom out a little bit. Of course, the camera will pass here without hitting the part. Carefully, continuing the inspection process stage by stage, checking for insert visibility, checking for bus bar visibility, in other words, checking for some kind of blemish in the part, some kind of white patch marks which indicates that the plastic has degraded, continuously instead of manual inspection. Once again, the process starts. It will check the sides of the part towards the end, the periphery of the part, keeps adjusting it without hitting anywhere else, now continues the inner peripherals, it continues a rotational scanning all throughout the part without hitting any other aspect. Sequentially, slowly, carefully, takes its time to ensure that each part that passes to the customer is good. Now it's done. The part is placed back onto the piece carrier. Back on workpiece. Quick and views now for this station. This is a quick demonstration of the critical submodules of the project as part of the non-PAT internship proceeds with Eckert Automotive India Private Limited by self, Vinod Vasan. We will start off with a quick run-through of the Hobson pneumatic subsystem simulation. In this context, of course, the simulation is already running for some time and the animation is started. The purpose of this is to emulate how a simplified distribution of the pneumatic components of the system could be. Of course, it could immediately be observed that these are hydraulic components, but being an open source software, pneumatic submodules are not available with Hobson. Therefore, our hydraulic elements have been included to emulate the overall implementation of a fluid pass system. Of course, we can see direction control valves, we can see proximity sensor emulation switches, we can have corresponding actuator systems, we have supply units, we have a pump, we have a tank, we have a pressure relief valve, corresponding distribution lines, volume units, of course, corresponding loads via translational masses, and so on. Of course, when the corresponding station, we have station 1, station 2, station 3, 1, 2, 3, and at this third station, we also have another actuator that's implemented for the inversion mechanism. Once the workpiece carrier comes into place, the sensor is triggered, the plunger reaches out, and of course the nozzle starts working and the workpiece carrier stops. Of course, the corresponding ultrasonic well detection test is happening as we speak. Once the process is completed, of course, the plunger will retract and the part will move forward. For the second station, once again, the plunger moves forward and the corresponding actions will in turn happen. We will have the corresponding nozzles in turn working for two reasons. One, the place where the part is rotating for the stress test to blow out silvos during rotation, and also those corresponding nozzles that are needed to clear the workpiece of any silvo as it passes along the conveyor system. Once this station is completed, of course, the part will move on to the next station since the corresponding plunger moves forward. The cadence controller kicks into action, and once the corresponding subroutine in the controller for the camera is completed, the inversion mechanism will be responsible for inverting the part for which a pneumatic subsystem is triggered, which will lift the part, first approaching it, and thereafter the controller for the camera will once again ensure that the camera is in turn continuing the detection process. Of course, this process is completed, everything retracts back into place and the process continues. Of course, we can have a visualization of all the key process parameters. We can check, of course, pressure corresponding to each element in the simulation for the corresponding timestamps. We can of course see the tank, so there's nothing. Then of course we'll have corresponding valves. We have 2x2 valves, 4x2 valves, 4x3 valves, direction control valves, and the graphs can correspondingly be visualized. Of course, in this context, for a corresponding valve, let's say we have a 4x2, and let's say we have a pressure, and this will be the corresponding pressure difference. Pressure build up when it's blocked, and of course a relief valve takes some time to kick in, and of course the relief of this pressure once the flow begins to happen, since there's no further obstruction. In this regard, this has been a quick overview of the preliminary Hobson simulation for the pneumatic subsystem. Going forward, we have of course an emulation of a basic or a preliminary PLC interconnection layout as well. This has been emulated using PLC Fiddle open source. This ladder logic diagram is divided into 3 subsections, from proximity 1 to proximity 2 as part of station 1, station 2 from proximity 2 to proximity 3, and the rest for station 3. As part of the first station, we will have proximity 1 triggered. The workpiece carrier triggers the proximity 1 sensor. A timer is triggered, and after a certain point in time, the plunger retracts out. The ultrasonic controller kicks into action. Once the subroutine is completed, the plunger will go back in. In between, when an auto-K weld is detected, but more specifically also when the subroutine is completed, a verification internal memory switch is triggered as well. Once this happens, the part moves forward since the plunger retracts back, and ensuring that of course the conveyor motor is running. Of course, the proximity 1 is off and proximity 2 is on. Once proximity 2 is on, the second plunger reaches out, stops the workpiece carrier. A gantry robot starts lifting the part from the workpiece carrier, puts it onto the stress test motor. The motor rotates, as you can see, for some time, and it stops. The gantry return home process will start once again, and in this process, of course, the gantry robot will return back home, and the part is placed back onto the workpiece carrier, and the process is in turn completed. Once this topic is over, of course, the gantry robot is deactivated and proximity 2 sensor is deactivated since the corresponding plunger retracts. Moving on to proximity 3, we have the third station since the workpiece carrier halts at that location. Of course, we have an on-delay timer, and the corresponding time is required for the stopper or the third plunger to reach out. The camera station kicks into action. After some time, as part of the second subroutine of the camera-based detection, the inversion mechanism inverts the part for any kind of short mold detection internally. And once that corresponding detection is completed, the entire process grinds to a halt and proximity 3 is off. And the process starts once again for the next workpiece carrier. Of course, the input modules are switches, proximity sensors, and corresponding internal memory triggers. We have output modules for the stoppers, for the motors, for the controllers, for the well test probe, and of course internal operational timers, all of which has been documented in full. Other significant aspect of this demonstration includes a distribution of transfer learning based, deep learning based, AlexNet based artificial intelligence condition detection modules. This has been consolidated over the air via a web server architecture over a dedicated website, the company website, which has been custom designed. So we log in with the credentials to access the functionality with the corresponding credentials. We log in and we see this page work. We have three models. One model for NDT detection, which will detect whether or not a certain well bead is okay or not. Run sulfur detection to check the quality of sulfurs, and short mold detection to check if a specific final produced part has a short mold in it or has a copper bar visible in it against a drum. It's important to note that as part of the functionality of Station 1, the output from the non-destructive testing probe, which it relays to the corresponding controller, will be linked with the execution of Module 1 in the master server. So when I run NDT detection, immediately we will see on the screen sample detection results popping up, as can be seen now. Of course, we can see that the good ones, or the good results, are those which are always elliptical, but the ones which are not so elliptical are obviously not good ones as well. Subsequently, we move on to the next detection. Run sulfur detection, where images of the sulfurs which have been extracted from the camera station at Station 3 are in turn correspondingly processed, and the outputs are provided as can be seen. Of course, the efficacy of the model can always be improved. In order to show the right results, trained on more images to give the most precise answers. Once again run, and we'll have the corresponding results. Moving forward, we run the same submodules for short mold detection. And we see the answer. Yep. So we have a good part to the left and a not so good part to the right because of this visible blemish and extra copper that is visible. So now we close this process and we log out, and the process comes to a halt. This has been a quick demonstration of the overall functionality of this specific set of submodules for this project. In addition, we can also see the overall functionality of the design via a separate presentation video. Thank you very much. This is a quick overview of Module 4 of the present project. This is the setup, which includes the Raspberry Pi, a camera, and the sulfurs from the assembly line that have been placed below for testing. This is the system that runs the server code, and this is the IP at which the program is running. The entire process flow is that this particular camera unit will detect flaws in these sulfurs as an edge device in the process, wherein it first captures an image and sends that image in an encoded format to the master server, which performs the image processing because it is powerful enough and capable of doing the same, and subsequently invokes a trained model if it exists or creates one if not, and thereafter provides the classification results back to the edge device, which then displays it on the screen. So we will run the process once as a whole. So we will run the module. As step 1, this program, the server is running and ready to receive a response from the edge device. So we run the module. The video feed starts from this device. Once the video feed is started, we press the button S. Immediately we receive an image. So we can see that in the back end we have one sulfur detected, second sulfur, third sulfur, fourth, fifth and sixth, all well detected. Each sulfur is individually extracted for its internal referencing. The model is trained, and subsequently a result is provided back here onto the device, because a model is already trained and it exists. If a model doesn't exist, it creates one and trains it on the required data. So we can see individually for each of the sulfurs that's present, we have the corresponding test results with their labels as to whether the punch mark is okay, or if the bend angle is okay or not okay. As a continued trial run, we can always have the process continue. So once the process is restarted, we have the live stream going on once again, as you can be seeing. So let's say I remove two of these sulfurs.
Now we have only 4. And if I press capture again, the information comes back, and now we can see the system adapts to the presence of just the 4 silphos. It's not hard-coded, it's adaptive. It segments the image accordingly and detects them, aligns them according to the required perspective, and proceeds forward. Now, once this is done, of course, and we go back to the terminal, once again, corresponding to this number of silphos, we have the results. Going back to the live stream, once again, maybe I remove 2 more silphos, push it out, and then we start again. And now we can see there's only 1 and there is 2. These are the 2 extracted silphos. It feeds the image to the model, and thereafter we can see once again that we only have 1 and 2 silphos which are being detected. So it not only detects how many silphos are there automatically, it thereafter extracts the required information from the image, feeds it to the model, and the model gives you a condition classification output for this specific application. Please note that these silphos are the actual silphos that come from the assembly line and are not just dummy silphos which have been designed